A warm welcome to everyone. Myself, Alan, and Sharon Amrita. Today we are going to take the topic Hamilton variation principle for non-holonomic system. So first of all, we will discuss about what do we mean by Hamilton variation principle. As last class we learned, Hamilton variation principle, the action angle is delta integral time t1 to t2 L dot dt, where L is the Lagrange. So, Hamilton variation principle is the fundamental concept in classical mechanics that provides a powerful framework for derivation of the motion of equations in any systems. It serves as the bridge between the classical mechanics and also the modern physics like quantum mechanics and general relativity. So, today we are discussing about how Hamilton variation principle is applicable for non-holonomic system. So, first of all, what do we mean by non-holonomic system? So, before going to non-holonomic system constraints, we should know the constraints. The constraints are the things that we are giving a motion or a system motion, a resistive force or something. So, we can divide the constraints into six types. So, the two most important constraints are holonomic constraints and non-holonomic constraints. Holonomic constraints are the constraints which can express everything in the position and time. There is no derivative forms, and also it is possible to integrate very easily. Example: the bead sliding on a straight wire can only move along the wire's direction. That means forward or backward. But in the case of non-holonomic system, this constraint not only involves the position and time; it also involves the velocity and higher derivative forms. So a common example we can say is a car moving in x direction. So to change the direction, to change the steer, we have to rotate the steer wheel. Then only it will change the direction. Or simple example, I would say a rolling wheel. Imagine a rolling wheel which is touching on the ground on x point, and it will rotate at an angle of theta. So whenever you're changing the angle, whenever you need to rotate it, the direction, the position is also changing, same as the angle. So we can say that in non-holonomic system, the two coordinate system are interconnected. They are not independent with each other. They are dependent. But in holonomic system, the constraints are independent with each other. If your x-axis is changing, it doesn't depend on the y-axis. That's why non-holonomic system is most important, because you explain the motion of systems like simple pendulum, the rolling of the wheel. We have to consider it as a non-holonomic system because the generalized coordinates and the virtual displacement are interconnected. To make it a proper equation, to make it and for analyzing the motion, we need the non-holonomic system. So let's go for the Hamilton variation principle. So we are considering the generalized coordinates are not independent, and also the virtual displacement are also not independent, which means generalized coordinates are interconnected with the virtual displacement. So straightforward, we can write for the constraints equation summation of aij dqj plus ait dt is equal to 0, where aij and ait are the functions of time. M indicates where I is equal to 1, 2, 3 to M, where M indicates it's a M constraints equation. We can write the form in M constraint equation. So we are explaining the constraint equation for the virtual displacement where delta Aij del Qj is equal to 0. Then we are multiplying it with a Lagrange multiplier. Lagrange multiplier is a constant. It doesn't have any quantities, but is used to ensemble the constraint to follow a particular law or a particular rule. So it cannot move out of that rule. So we are multiplying with lambda I, which is an Lagrange multiplier. We know the Hamilton principle action angle is del integral 1 to t 1 to 2 L dt. We are using the Lagrange formation in Hamilton principle. So we can write instead of L the Lagrange equation dou L by dou Qj minus d by dt of dou L by dou Q dot j into del Qj is equal to 0. So let us consider this is our first equation, and we can consider this as our second equation. So we can say the Hamilton variation principle is connected with the constraint equation for the virtual displacement. So we can take the sum of the both. So we can say that integral time t1 to t2 dt summation of dou L by dou Qj minus d by dt of dou L by dou Q dot j plus summation of lambda I aij into del Qj is equal to 0. So next part will be taken by Sharon. How the Hamilton variation principle for non-holonomic constraints can be used.
Thank you, Alan. From the above equation, we can generate 4 points, which is the selection of Lagrange multipliers lambda i's are at our disposal. Delta qj's are still not independent because they are connected with m relations. They are connected to m number of constraints. So when we subtract the m number of constraints from the n number of generalized coordinates, we will get the independent coordinates, which is n minus m. The remaining m are fixed. The integrand in the above equation can be split into two as integration of 1 to 2 dt summation of j is equal to 1 to n minus m of dou L by dou Qj minus d by dt dou L by dou Qj dot of summation I lambda I aij of delta Qj plus integration of 1 to 2 dt summation of j is equal to n minus m plus 1 till n of dou L by dou Qj minus d by dt dou L by dou Qj dot plus summation of I lambda I aij of delta Qj is equal to 0. So as we know that the values of the lambda i's are at our disposal, the second term vanishes, that is it becomes 0. This term vanishes, that is dou L by dou Qj minus d by dt dou L by dou Qj dot plus summation of I lambda aij is equal to 0. Here the j value is from n minus m plus 1 till n. Now we will be taking the second term, that is we are free to select the n minus m coordinates arbitrarily, and therefore dou L by dou Qj minus d by dt dou L by dou Qj dot plus summation of I lambda I aij is equal to 0. Here the values of j is from 1 to n minus m. So combining the above two equations, we will be getting the complete set of Lagrange's equation for non-holonomic systems. So we will be getting dou L by dou Qj minus d by dt dou L by dou Qj dot is equal to minus summation of I lambda I aij. When we multiply this equation with the negative sign, we will be getting d by dt dou L by dou Qj dot minus dou L by dou Qj is equal to summation of I, the values from 1 to m, lambda I aij. The j value is from 1 to n. Now we have n plus m unknowns. Here n is the number of coordinates and m is the number of Lagrange multipliers. As we know, the Lagrange multipliers ensure that the constraints are under the system. So when there is n number of constraints, there will be m number of Lagrange multipliers. So the above equation together with the equations of constraints now being written as a first order differential equation, summation of j aij qj dot plus ait is equal to 0. This constitutes the n plus m equations for n plus m unknowns. So at last, we will be considering the physical significance of the undetermined multipliers. So for that, we should remove the constraints on the system in such a way that we introduce the external forces capital Qj. So by the application of the external forces capital Qj, the motion is unchanged and the equations of motions of the system remains the same. Under the influence of these forces, the equations of motions are identical with the previous equation. So we can identify with Qj the generalized forces of constraints. So this equation now becomes as this equation, that is d by dt dou L by dou Qj dot minus dou L by dou Qj is equal to capital Qj. So thus we complete the derivation of the non-holonomic Hamilton's variational principle. Thank you, sir.